For those of you who don't know me, I'm Giulia Foscari. I'm an architect. I used to teach here at the AA until last year, diploma unit. And I'm now co-directing with Francesco Bandarin, who's sitting there in the front row, the AA Polar Lab. Some of you might have wondered what was this sort of thundering sound in the background as we were all coming in the lecture hall. Well, that's a soundscape of the southernmost continent and territory of our planet. The seventh continent, so often neglected by our sort of collective consciousness, but also, to make a sort of banal example, from the Google search engine, which conveniently omits Antarctica from its normal general worldview. And if you sort of zoom in relentlessly trying to find information in Google Maps, you'll actually still find a sort of pixelated collage of images that reminds us of the blank imperial maps, denouncing unequivocally the striking contradiction between the hypermediated image we have of Antarctica and, on the other hand, the troublesome ignorance that in a way surrounds it. But the sound could also be interpreted as a territory's response, or in a way the lament, to the anthropogenic climate change, as it sort of amplifies and echoes the sound of the crevices, of the formation of crevices, and of the carving of ice that we all know is one of the quintessential markers of climate change. Tonight is a real honor to introduce to you an architect that has accepted the challenge of building on this living ice. A colleague who has understood that human presence in Antarctica, which is an achievement which is approaching its 200th anniversary in 2020, is essential to be in the position of building accurate scientific models that allow us for reliable predictions of the future of our planet, and has therefore collaborated with countries and their respective scientific organizations to build scientific stations on the continent. I'll refrain here from sort of indulging too long of an explanation on the extraordinary site in which Hugh Broughton and his team has been working on and operates daily, but I'd still like to show a few diagrams which were produced by some of the students I see here in the room tonight within the context of the recent AA Polar Lab workshop we conducted in collaboration with Accurat. Antarctica, really briefly, is, as you can see, the continent is almost as large as Australia. Its territory is defined geographically by the convergence, which is ultimately a current, where the cold currents and waters of Antarctica meet the slightly warmer waters of the sub-Antarctica. And politically, it is defined by the latitude south of the 60th parallel. The national claims that some of us might remember that were made by 7 countries between 1908 and 1942 are somehow suspended since the signing of the Antarctic Treaty, which is effective since 1961. Here you see sort of a first attempt at diagramming its operation, but it basically is a pinnacle of the sort of, it's a fragile governance system which prescribes that Antarctica is a territory which is devoted to science, solely to science. There's no military activity which is allowed, and no resource extraction neither. But during these sort of past years, there are 53 nations that have in the meantime embraced the Antarctic Treaty system, leaving approximately 143 countries still unrepresented. The territorial footprint of these sort of national investments is manifested into 77 research stations that you can see punctuate the continent, mainly on its coastline, but also within the middle of the territory. And most of these have been rebuilt or extended throughout the years, as this timeline attempts to show. And most of them also have been built in proximity to historic sites and monuments, which are marked here on the map, and their respective protected areas. Some of these include, obviously, the sort of heroic era huts that you might be aware of, Shackleton and Scott, just to name a few, but they're also a rather eclectic list of other artifacts which are part of this preservation list. And yet all of the stations vary, or most of them vary in typology. It depends primarily on the altitude where they are located, the climatic condition, and obviously the ground upon, or the ice upon in some cases, in very rare cases, ice sheets, as we'll see with Hugh tonight, upon which they are built. They also vary in size and programmatic specifications, as well as number of buildings. You can see on the upper left, for example, McMurdo Station. It's a US station. It's arguably a small town or a small city. It has many buildings. In total, there are 1,289 buildings in Antarctica, which account for a total surface area of approximately 211 square meters. So let's say 3 Louvre, just to give a scale comparison. And all in all, they can sort of host up to 4,800 people during the summer months. But how do these researchers live? How can architecture provide more than a temperature-controlled environment that allows for survival in such an extreme condition? As a side note, the lowest recorded temperature in Antarctica was of minus 89 degrees, and the highest wind speed 327 kilometers per hour. And again, how can architecture mitigate sort of the symptoms of what is called polar depression, or so-called polar depression, i.e. also the psychological and physical disorders that emerge or can emerge through long exposures at darkness during the wintertime, and isolation and intense cohabitation models. So all of these questions were questions certainly answered or posed within Hugh Broughton's team and addressed while building Halle VI, which we will certainly see tonight for the United Kingdom, Juan Carlos first for Spain, while sort of redesigning or designing Comandante Ferraz for Brazil and Jambogo for Korea, and rethinking at present the Scott base for New Zealand and expanding it, as I just understood, and Rother again for the UK. But given the trajectory of Anthropocene and the sort of ever-increasing possibility that humankind might have to inhabit exponentially inhospitable territories, I believe it's really a true pleasure to have tonight the opportunity to invite Hugh Broughton to share with us his experience on Antarctica. The unconventional brief that Hugh was confronted with offer new perspectives to our discipline and encourage the development of experimental prototypes, of which here at the AA especially we're immensely fond of. So it's a very real honor to invite Hugh up on the stage now to contribute to not only to launch the AA Polar Lab session and conversations, but also to contribute to the new canonical history series of the AA. Please join me in welcoming Hugh Broughton.
Thank you so much. That was such a nice introduction, and I actually have to admit I learned quite a lot during that, so that was really cool as well. And some beautiful, beautiful diagrams as well of all the different stations that, I could imagine will be very useful in some of our presentations in months to come. My brief this evening is to talk to you about the extreme challenge of building in Antarctica, drawing upon some of the experience we've had over the last, it's now 15 years since we very first became involved in the Halle project, and then working on other projects since. Of course, I'm sure you're all aware, Antarctica is the coldest, windiest and driest of the continents on Earth, and yet holds 90% of the world's fresh water within its region. This is in fact an aerial view of the Antarctic taken by NASA, and you can see those areas which are green, which hold land underneath, and those areas which are light blue and darker blue, which are essentially ice shelves, which is thousands of year-old ice frozen between the land masses. And there is a sort of popular thing that you can do looking up on the internet, what happens if all that ice were to disappear, and this would be the archipelago that we would be left with. The reality is that if all that ice melted, then sea levels in the world would rise by around 60 meters. But the safe aspect of that is that it would take in excess of 5,000 years for all that ice to melt. So it's not something that any of us probably experience. But what we may experience is the demise of large sections, and in particular the Western Antarctic ice sheet, which is one of the most dynamic in the Antarctic continent, and which is held in place by a series of glaciers that, if they were to disappear, would allow the ice sheet itself to start moving at great speed into the ocean. And that in itself could lead to sea level rises of around 3 meters, which may not sound so much in the context of 60, but certainly would have a significant effect around the world. From our own perspective, we've been very lucky to be involved in a series of different stations at different levels. Most of them have involved some degree of architectural competition, and probably more than half of those we've lost. So it might look like a lot, but actually in the end I think there is certainly a good chunk that we have been involved with, but others which we've spent months and months preparing proposals for that have then led to other people building them. The one I wanted to focus on in particular is the British station, Halle Station. We designed Halle 6. That's because there were 5 before, most of which disappeared. They were either buried or the last one had to be dismantled. Halle is a really unusual location. It's on a floating ice shelf. Most of the bases in the Antarctic are founded on ground. It's at 75 degrees south, which means it's about 900 miles from the South Pole. This is the view of the previous station, Halle V. So Halle V, by the time it was dismantled, comprised around 4 or 5 structures. But the base components were these 3 buildings. The largest one on the top right was called the Laws Building, and that was the main sort of habitat of Halle V. So that's where all the bedrooms were, the dining, recreational spaces, and many of the office spaces. And the other 2 buildings, the Piggott and Simpson platforms, were where the science was conducted. So one did science sort of near ice science, and one did atmospheric and outer atmospheric science. And it was one of the kind of key social issues of the base was that there were 2 groups of scientists studying relatively related subjects, but working totally independently. And that was alongside the technical challenges, one of the sort of social challenges that our project presented. The sort of great sort of geographic and environmental challenge of Halle, however, is that it is on a floating ice shelf. So that's ice that's 150 meters thick, which has flowed off the main continent of Antarctica and is supported by the Weddell Sea underneath, and which was moving at quite some rate, at a rate of around 400 meters per annum. So it's a very, very dynamic site. And although there are 2 other stations which are located on ice shelves, they were moving at fractions of that speed. So this diagram just explains the concept of the ice shelf, where the ice has flowed off the main continent, supported on the ocean. And it also explains one of the other key environmental challenges of building at Halle, which is very, very high wind speeds, because you get cold air building up on the center of the plateau of the Antarctic, and then that air, as it drops down towards the ocean, then picks up speeds and creates very high winds known as katabatic winds, which then carry with them ice and snow particles that cause massive, massive drifting around anything that's left on the surface. So this is the view of Halle V. So it was a very pragmatic structure, more akin perhaps to something you might find in an oil field, supported on 20 steel legs. This was the main habitat building, that were jacked up every year to keep it raised above the snow. The snow levels rise at Halle by around 1.5 meters every year as a consequence of deposition, but mostly as a result of drift. And it was a single-story timber structure. This was one of the science buildings. Actually, this was the last time this one was lifted before it was eventually decommissioned, and quite lonely in a way, sitting in that huge expanse of the Brunt ice shelf, just flat white ice pretty much as far as the eye can see. So the challenges of building in the Antarctic are obviously pretty apparent, the coldness in particular. Temperatures at Halle go down to around minus 55 degrees Celsius. So there are other stations that are colder. Vostok Station, for example, I think has had temperatures down to at least minus 90, and at the South Pole also there are temperatures in the minus 80s. But minus 55 is still pretty cold. Everything will freeze, your eyebrows, your breath, everything at that temperature. In the middle of winter, the snow and ice will freeze solid on anything you leave outside, so your vehicles that you're using in the summer become totally unusable in the middle of the winter. And then in the summer, when the temperatures rise, so also the regularity of high winds increases, and temperatures at Halle, wind speeds at Halle in excess of 100 miles an hour, or around 150 kilometers an hour, are not uncommon. And they will carry significant drift with them. So they'll pick up ice particles and snow particles, and they will bury just anything that's left on the surface. So if you leave a small tool for your construction, that will get buried. If you leave a vehicle, eventually that will get buried. And if you even leave a building, eventually that will get buried. So you need to come up with strategies for how to deal with that. As I said, the combination of the wind and the drifting snow and also precipitation of snow meant that at Halle there was 1.5 meters of snow every year. And the only real benefit of that is that if you do leave things on the surface, then you create little mounds or drifts of snow just behind, which are really good fun if you're just practicing your downhill skiing. And this, for example, is our structural engineer just on his first ever outing on skis, hopefully. Oh, not found. Oh, well, you're going to have to miss out on that. Do you think the media may be misconnected somehow? Yeah. Maybe we'll try one of the others later on. Was it? Yeah. Says not found for some reason. Doesn't matter. We'll carry on. Okay, doesn't matter. Anyway, you would have seen he wasn't very good at skiing. So every year at Halle V, it was necessary to jack the building up to account for the rising snow level of 1.5 meters. And the way that that was done is that they would create baskets using scaffolding tube around each individual leg, and then there were small electric engines that would then be put on the legs, and they would just jack the steel work up within that leg, and you would have to put bolts in, then jack it a tiny bit more, put the bolts in, move them up, jack it some more. And it was a really laborious process. Took at least 2 or 3 days just for this building, and a day each for the other buildings, but involved every single person on base. All science had to stop, all other operations had to stop. Obviously, you're working with steel bolts and things. When we went on a visit, we had to help with this process. And it was really time-consuming and extremely cold. Fine when the sun is shining on you, but the sun tracks around the building. And when the sun moves off, then you get incredibly cold when you're doing this process. So there's a challenge of cold, there's a challenge of wind, there's also the challenge of social isolation, living in such a remote location. And in Halle V, these were the interiors. So I don't think there had been that many architects involved in the creation of Halle V. It was fairly institutional. It was also divided up into a lot of cellular rooms. So, for example, you'd have the TV watching room on the right-hand side, and I always really admired this because they would buy box sets of different things, and then they would just watch one episode a week. They would never binge on box sets. They would be really rigorous. The other thing is they had the bar, and the bar was also a separate cellular space, and that creates a lot of social issues with people, particularly in the winter, just spending all day drinking in the bar. And then you'd get other people who would feel really disconnected from the group, felt unable to enter these rooms when there were fun things going on, and they would just walk up and down that corridor and develop what was called the Halle stare. So there's quite a lot of kind of psychological challenges of living in this extreme environment which needed to be addressed in any new design. Added to that, of course, in the Antarctic, it is dark for a large portion of the year. It's actually, the sun doesn't rise above the horizon at Halle for 105 days in every year. At that point, the station is totally isolated because the sea ice will have frozen for up to 200 miles out from the continent, and there's no way to bring ships in, and it's way too cold to fly planes in. So the 15 people on base are, even though they may have contact with the outside world, are certainly physically isolated. And the only escape they have from the station is to go on small trips to visit their neighbours. So they reach the edge of the ice shelf, then they rope up, abseil down, and then they go and see the people who live nearby. And there is a really massive colony of emperor penguins just around 5 to 10 miles away from was the site of Halle V, a little bit further from Halle VI. So it's a challenging location. Everything that is needed to supply the base has to be delivered by ship. The ship can only get close to the station in the summer months. So around about Christmas time, this was the British logistics vessel, the Ernest Shackleton, arriving at the edge of the sea ice, then unloading everything onto the sea ice, and then from where it's dragged up to the ice shelf, where the bulldozers are used to manipulate the ice to create ramps, so that then everything can be then dragged up onto the ice shelf itself and across to Halle. The sea ice is very, very fragile. It's around 2 meters thick, and you can't put anything on it that weighs more than around 9 tons. So people always say, oh, why did you not build the station in its entirety and deliver it? It's because it all had to be delivered onto the sea ice, and the maximum load was 9 tons, which is only the fraction of a size of a building. You'll see later, but one of the modules at Halle weighed around 100 tons, so everything had to be broken down. There are some places where the ice shelf does come close down to the sea, but they're a very long way away from the site of the station. This is one of those. It's a creek called N9, which was occasionally used for resupply. In terms of plane, the station is so isolated, and there's only an ice runway which is not constantly tracked over by bulldozers, so only planes with skis can land there, and generally only these small twin otters, which carry about 5 people. The flights, maybe sort of 4 or 5 flights a year from the other British station, Rotherham, so again, adding to the sense of isolation at the base. So against that whole background of isolation, cold and wind, you might think, well, why would the British Antarctic Survey want to be working in a place like Halle? And eschews the crudeness, but it's pretty simple. It's because the science that is conducted in many of these research stations is leading our understanding of things as basic as global warming. So, for example, it was in the 1980s that 3 British scientists first discovered the hole in the ozone layer at Halle, which subsequently led to the Montreal Protocol banning the use of CFCs, which is probably to this date one of the most important pieces of environmental legislation conducted globally. At Halle also, there is significant research carried out into the interaction between the Earth's atmosphere, the outer atmosphere, and the sun, into magnetism, and it's part of a whole network studying global weather, which has significant impact, as I say, on our understanding of how the Earth's weather systems are operating. But around about 2000, a major issue was discovered. The Brunt ice shelf on which Halle V was located is very dynamic. It's flowing out to sea, but it's lodged in a couple of places. At the top of that red line, it was lodged against some rocks, a rocky outcrop called the Rumpels, and at the bottom it became close to where it was connected to the main continent. And crevasses were seen to be forming in those locations, with the prediction that a huge iceberg, the size of a small English county, would probably break off from the main Antarctic landmass and leave Halle V on the wrong side. And of course it had its legs frozen in the ice, making it more or less impossible to move, possible to remove, but not possible to move. And as a consequence, the British Antarctic Survey decided to hold, it was a first for them, an architectural design competition for the new station. So they put out an international call. They had around for multidisciplinary teams to come up with combined engineering and architectural solutions. And they had around 90 entries initially. It was quite funny because at the time we were just a practice of 4 people, and we were working out of a small shed in West London. And I remember hearing it on the radio about the requirements for the architect that they were looking for at the time. And they said they had to be multinational, multidisciplinary, world leaders in sustainability, world leaders in prefabrication. And I remember listening to all 4 of them and thinking, well, that's so straightforward, because I am not able to do any of those things. But still, I went along to the launch, and I met an engineer from AECOM, who many of you may know is a big global engineering consultancy. And the engineer there, at that time, they weren't into architectural competitions in any way. And he sort of pleaded with me to enter with us, and I pleaded with him to let them lead the bid, which eventually they did. And we were really lucky. We found an engineer based in Colorado Springs in the US who had spent his whole life working on the American polar program. And we paid for him to come over to the UK for 48 hours, and he gave us a kind of crash course in all the things that you should and shouldn't do in Antarctic design. And he made sure that our sort of naturally ventilated building with wide opening windows bit the dust as quickly as possible. And eventually we got the kind of core bases of a design sort of together, and it was, I guess, from that springboard that we eventually won the competition. But before I show you our designs, I thought it's worth just positioning the building in the context of Antarctic architecture. We were having a really interesting conversation just before this about the date that Antarctic architecture starts. And it's a very difficult one to position, but certainly some of these old huts are quite unique in their ambience, but also in the preservation of their fabric, but also of the elements within them. So this is Scott's Antarctic hut from his first expedition, which was actually an uninsulated building, so cold in fact that when they had put it up, they found that they couldn't stand living in it. So they actually lived on the ship, the Discovery, and used this just really as a storage facility. But it's preserved fantastically. It has actually undergone significant conservation by the Antarctic Heritage Trust, but still contains many of the objects from that original expedition. This is Shackleton's hut, which is also on Ross Island, which is a lot more sort of, has a much pleasant, sort of more pleasant demeanour about it, I guess. Was insulated with cork, and their guys all slept within a communal space. They cooked in within the communal space, and it was from here that he set off to the South Pole, reaching within 90 miles of the South Pole before turning back. And that, on the bottom right there, that's Mount Erebus, which is an active volcano. And then this is the Scott hut from which Scott did reach the South Pole but didn't return, the hut at Cape Evans, which is again a timber construction, the timber beautifully preserved, but again it has undergone significant conservation. And then more recently, particularly from 1957, there was the International Geophysical Year, when a number of buildings were erected in the Antarctic to facilitate science. This one was built as part of the Trans-Antarctic expedition when the British and the New Zealanders were intending to kind of, well, the New Zealanders were going to help the British to cross over from one side of Antarctica to the other. The New Zealand portion of the expedition was led by Sir Edmund Hillary shortly after he'd climbed Mount Everest, and he was so full of energy that he actually reached the South Pole before the British. And he built the Scott base, which is the most remarkable structure. They decided to build it, and 357 days later they had fully completed it. And it was a series of interconnected huts connected with tubes, of which one of them has been recently restored, Hut A. You can see in its original colours on the top left there, and on the top right with its original colours, many of the things from within inside the building still beautifully preserved. And from the same era is the first Halle I, which was built as a very simple timber hut. Here we're seeing it probably around 3 years after its construction, so the snow level has risen 1.5 metres per year, is now up at the eaves. They continued living in it for quite a few years after this by climbing down shafts into the building until eventually the ice crushed it. They then decided, well, because their buildings are getting buried by the ice, the best thing would be to design buildings to be buried. So Halle 3 on the top left and Halle 4 were both built as tubes which could be buried by the ice, but they had very, very short lifespans, primarily because the ice on the Brunt Ice Shelf is so dynamic and moves in a way like water, and the ice just crushed the buildings. You also have to just imagine what it would be like having to climb down to where you live, down a ladder in one of those tubes. Imagine the smell of the sewage, of the generators, of the old food, no views out of the building. It was a pretty inhospitable place to live. This is actually the last view of Halle 3 when it was crushed by the ice shelf and then spewed out into the ocean. This was actually seen by people on the Bass ship around about 15 or 16 years ago when they saw the remains of Halle 3 being spewed out into the ocean. More recently, there have been some more dramatic and contemporary structures built in the Antarctic. Probably the best known of all is the Buckminster Fuller Dome at the South Pole, which was a geodesic dome within which structures were placed and which was removed only around about 15 years ago. The most recent generation of Antarctic buildings have all tended to be elevated so that they don't get buried by rising snow levels and so that they allow the wind to flow underneath, minimising the amount of drift and therefore the amount of management that's needed with bulldozers pushing snow around the place. Here are just a collection. On the bottom right is the Belgian base, Princess Elizabeth, which is a summer-only station and pertains to be a zero-carbon station. On the bottom left there is Neumayer 3, which is the recently completed German station, which has a very sophisticated hydraulic system for lifting it up above the rising snow level. The top right is the American base, Scott Amundsen, which also has a system for raising it above the snow level, but although the snow rise at Scott Amundsen is fairly minimal, only around 300 millimetres per annum. And then on the top left is Concordia, which is the French-Italian base. And I am reassured that the French and the Italian, they don't have one is ones and the other is the Italians. Actually, they do kind of meet and do stuff together in the two buildings. But the challenge with Halle always was that not only did it have to deal with the rising snow levels, but it also had to be relocatable so that in the future it wouldn't disappear on another iceberg. Well, so was the theory. I'll come to that a little later, but the point is that it needed to be relocatable. So we had to break with this concept of a big structure on hydraulic legs and divide it down into a series of modules, each on hydraulic legs and each supported on giant skis, so it could be disconnected from a line and moved to a safer place inland if ever there was the threat of the site disappearing on a giant iceberg. So we came up with this concept of standard modules of 160 square meters each weighing between 80 to 100 tons, which could be used for science, they could be used for office spaces, they could be used for bedrooms. There's 8 bedrooms in each one of these modules. The bedrooms are all bunk bedrooms, so that in the winter everybody gets their own room, and in the summer you share a room. The idea with the bedrooms was that they should be reasonably comfortable, but not so comfortable that people kind of hide away from the community, because you want to try and bring the small group together to support each other. And then just with simple things like good natural lighting, good artificial lighting. So we worked with our lighting designers and with Philips to develop an early version of a kind of sad lamp with an alarm clock function to help reset people's biorhythms, boost their serotonin production so they don't suffer so much from the winter blues. We also worked with Angela Wright, a colour psychologist, who helped develop for us a special palette of colours for use within the building, again to try and address issues to do with seasonal affected disorder. And we then exploited what natural light there was, particularly in the summer when you get great natural light, to make sure that even though the buildings might have to be arranged in a line to respond to the prevailing wind and the potential for drift, but that nonetheless each one of those buildings could, in a very simple architectural way, become a kind of destination in its own right. So we widened out the circulation, we used the colour to define one module over another, and we also raised up the ceilings to allow natural light through the roof so that you get these kind of well-lit hearts to each one of the buildings. And then as you get to the transitions, the circulation narrows down, and then there are points at those transitions when you can then look out onto the icescape all around. So the buildings actually narrow down for multiple reasons. A, so you can get the views out. B, for aerodynamics. And C, so that the linking pieces between could be kept as small as possible because they were very expensive to develop. The modules all have a base structure which is a steel space frame so that all the building services can run through that zone and be kept within the insulated envelope. And then the perimeter structure, there has a perimeter superstructure so that within the buildings all the partitions can be reorganized in the future, because the building has an expected lifespan of 25 years, but the science programs change every 5 years, so you want to be able to reconfigure the interiors on a fairly regular basis. The same modular approach was used for energy. So we have 2 of these energy modules which contain the generators which create electrical power and the heating. And we have 2 so that if one breaks down, then you can rely on the other. And they contain, alongside the power generation, they have things like water production plant, sewage treatment plant, fire suppression systems, waste treatment facilities, that kind of thing. And here you can see some of the services running through that space frame substructure to the buildings. And the idea of being on the hydraulics was that when it came to relocation, each module could be lowered down on its hydraulics and then dragged using the skis, using bulldozers to a new location where the station could be re-established. So through that sort of whole concept or methodology, we were able to accommodate all the requirements of our brief for science facilities, for for sleeping spaces, working spaces. But the one thing we couldn't accommodate was the sort of primary living space. We wanted a place where you could have the dining, recreational facilities, the kitchens, where everybody could come together. So for that, we developed a special two-story module, weighing now up to 200 tons and arranged on 2 floors, which had open plan space for dining, for the bar on the lower level, and then quieter cellular spaces on the upper level for watching TV, internet access, the gym, and so on. And this was a drawing from the competition stage, where we recognized that all these people working in the Antarctic were really into the outdoors. So we thought, oh, well, we'll give them a climbing wall to go from the lower level to the upper level. And then it was at that point that the health and safety officer from British Antarctic Survey pointed out the proximity of the bar, and a vote was taken on whether it would be climbing wall or bar. So the climbing wall bit the dust, unfortunately. This is the arrangement. So the building is arranged in a straight line because the predominant wind blows 95% of the time from the east-northeast. So the buildings are in a straight line so that the wind blows underneath the modules and then creates drift on the leeward side that you then don't have to bulldoze. And it's split in two so that if ever there's a disaster on one side, you've got somewhere to escape to until you can be rescued. And as it could take many, many months to be rescued, you need decent facilities in which to stay safe. So on the left-hand side, there are 2 science modules and an energy module. And on the right-hand side is the kind of the living space and another run of the energy modules. So there's that split with a bridge link. The idea originally of that was that it would be just a sort of for operations and maintenance, but actually the scientists, even at minus 55 degrees Celsius, in their T-shirts and shorts, will do the 25-meter dash from one side to the other as part of their kind of like induction to working at Halle. This just shows some of the wind engineering that we went through to predict where the drifts would take place. The idea of the snow management is that this is the profile of the snow that you'd expect after a year. So you'd have 1.5 meter of accumulation on the right-hand side and a big drift occurring on the leeward side because the wind has blown underneath the module and is creating this big drift on the leeward side. And then to raise the buildings up, what happens is the bulldozer comes along, pushes snow under each foot, and then the hydraulics is used to jack it up, and then the bulldozer pushes snow underneath, and now it's ready again for another year of high winds and deposition. In terms of the envelope for the buildings, one of the things was always impressed upon us is that in the Antarctic, what you don't want to do is be inventing things for the first time. It's fine to come up with innovative ways of combining existing concepts, but it's not a great idea to use the Antarctic as a guinea pig for something, because the people who are there have no recourse to any other form of safety. If something goes wrong, they are stuck there. Nonetheless, we wanted to push the boundaries to reduce weights and also improve performance. So for our envelope, we looked around and we saw that some of the more cutting-edge stations in the Antarctic were using glass-reinforced plastics for cladding systems, the benefit of which is that it could be made in big panels and erected quickly. And these are just some examples. There's a South African base at Marion Island, the French-Italian base at Concordia, the South African base on the bottom right, sits on this dramatic escarpment, that's Sanai 4, and then that was a small summer sleeping module at the previous Neumar 2. I'm not going to go into that. The principle of the base, however, is that it would be really well insulated with very low levels of air infiltration. It would use a vacuum drainage system to significantly reduce the amount of water usage, so that flushing the toilet it takes only 1.5 litres of water compared to 9 litres in a standard toilet. We'd have sewage treatment systems, which meant that the sludge could just be incinerated and otherwise the clean water could be dropped back in the ice. We used combined heat and power generators so that the heat that's given off to make electricity is used to heat the building. So every step along the way, we were using existing technologies, but in new ways to really drive the sustainability of the base and above all, drive down fuel usage. And that's been one of the great successes of Halle, is reduced water usage and reduced fuel usage per square metre compared to the previous station. So in terms of the construction, before we started out on site, we need to do loads of testing because it's one of those places, if it goes wrong, then you are really screwed for a long time. So much so that you may have to abandon the whole summer season of construction until you can sort your problems out and come back the next year. So one of the key things, of course, with Halle was proving the relocation strategy. So we had this test sledge made, loaded it up with cranes, tried the skis in different formats, tried pulling it with the bulldozers, and then when we were happy, then that determined one of the key elements of the design, which was the positioning and the size of the skis. We had loads of samples made of the cladding to test its ability to resist the high winds and the sort of sandblasting effect of the ice, but also a thermal shock. And then finally, we built test modules. So this is one of the standard blue modules where we put the frame up, we put all the cladding on, loaded it up with tanks of water to simulate the actual finished weight, and then tried out the hydraulics. And then we did the same with the big red module. And this is it, and it just shows the benefits, because you might see just to the left of the window there's a kind of panel out of alignment, and so we were able to strip that off, get it reset, put it back on again very easily in Cape Town where the cladding was made, but it would have been a disaster if we'd discovered that in the Antarctic. This photo was quite fun because literally just as I was taking it, I heard this massive big crash, and I thought, oh my God, one of the panels has fallen off on the rear of the building. So I went rushing round, and in fact what I discovered was that there was 2 cars rubbernecking the building, and they hadn't noticed that they were actually on a collision course and just smashed into each other. And it was a very odd sight in a sort of low-rise residential district in Cape Town. So once everything was ready, everything was brought together in the docks in Cape Town, loaded onto a Russian ice-strengthened cargo vessel, the Anderma, where it was then sailed for 15 days across the roughest seas in the world until it arrived at the edge of the sea ice, where the largest component, the space frame of one of the modules, weighing 9 tons and with some special skis and smaller legs attached to it, was unloaded and then dragged using big plant across the sea ice up onto the ice shelf. And here you can see some of the first steps of the construction. So the top left, that's what arrived at the site, and then it was lifted by crane onto some shipping containers, and then you were able to insert the hydraulic legs and the skis, which act as the means of relocation, but also the foundation. Those couldn't be installed to start with because they're really heavy. And then from that position, the prefabricated floors were installed. Then we inserted prefabricated services. All the generators and the fuel tanks went on. Then the superstructure. Some of the other buildings, we had all prefabricated rooms. So we really made the most of prefabrication on this project as we absolutely could. And one of the bizarre things when the building finished and I did the snagging is there were just no surprises because we had seen absolutely everything in factories around the world beforehand. Here you can see some of the modules in a line. So it was made next to the site of Halle V so that the construction crew could use the existing base to sleep in and for eating, and also the benefit from the use of the British Antarctic Survey's doctor and so on. Once all the interior prefabricated rooms were loaded on, then the superstructure went on, and then large cladding panels, and this is one of the largest going on, so it's the whole sidewall of one of the modules, which is around 3.5 meters high and around 10.5 meters long, all with the glazing installed, triple glazing, with very high degrees of sort of solar coating to stop glare from the ice. And here you can see the big red module, with some quite delicate construction going on here, which is a big glazing element to the centre of the building. The buildings were built in a way like you would fabricate a car. So we had a team doing steel work, another team doing cladding, and then one team dedicated to the red building, and then eventually moved into the different phases of the interior fit out. And then when the buildings had all of their exteriors finished and the interiors probably sort of 50% finished, they were linked up to bulldozers, dropped down on the hydraulics, and then dragged 15 miles to the eventual site where they were all linked together. And that's the view of the big red module moving off to site. And
Monday morning arrived.
This is a video showing that relocation.
And almost ready to go.
I'm convinced it's going to move from this location. I think the difficult part will be actually bringing it into line for the triborgs.
It's going to be about 160 tonnes. We're definitely over 200 tonnes with it. So just out of our comfort zone slightly. But good team on the job. If anybody can shift it, we can. Hopefully.
Surprisingly, it pulls out relatively easily for a 200-ton building.
So in a minute the camera pans round, and on the horizon you can see a little dark speck, I think just off to the top right, and that is the site of Halle VI, where the module was headed. They had to drive across this route multiple times to compact the ice so that it would take the load. And they had these 3 bulldozers behind for 2 reasons. They're in that formation, one so that if the building gets grounded they can help push it out, but also the head of vehicles was a massive Top Gun fan, so he took that opportunity for... And here we see all the modules linked up together and now ready for occupation. So this is a photo taken in around 2012 when the station was complete. And that's what it looks like on a normal day. This is what the average walk back from the vehicle workshop for lunch is like. So fairly lonely and a little inhospitable. The connections between the modules are flexible, so to account for sort of settlement, but also as you lift one building up next to another. And we got these made by a company that normally make connections between train carriages, and they make them in the Arctic to go down to around -50. And so they have microfoil insulation in. This is within the actual space frame itself, checking all the services. Just a view looking down on the building. And this is the south end, which is the science modules. The southernmost of the buildings actually has an observatory on it, which is for checking the weather. And it's also where measurements of ozone are taken. So this is within that observatory where they're continuing the measurements of ozone, which the depletion remains, but the level of depletion is decreasing. And that scientist there is using a Dobson spectrophotometer to carry out those measurements. This is within some of the science spaces. So it's a fairly robust working kind of space. Very flexible. You need to be able to add science equipment, take it away according to what experiment is being carried out at the time. In terms of the water production at Halle V, it used to be a bit of a team bonding event because you would have to go out with shovels and you would shovel the snow down a hole into a kind of buried giant kettle to create all the water that was needed for washing and for drinking, which was kind of quite good fun on a summer's day. It wasn't so good fun in a 100-mile-an-hour wind when people had to wear helmets to cope with the blasts from the ice. In the new station, it's much simpler. There are these 2 tanks. They have a hydraulic lid. The snow is pushed in. It melts. There's 2 of them, so that if one fails, then you can keep the other one going. The MT stands for melt tank, but I only afterwards realised how ironic it was that a water tank should be called empty. These are the toilets. So we have a vacuum drainage system like you get on an aircraft or on trains, which saves an enormous amount of water. This is within the plant rooms where the sewage waste is incinerated, and the fresh water can just be dropped back into the sea. This is the main living module. So the white glass is actually a highly insulated glass using nanogel, so it has a very good level of thermal resistance. And then the black glass is actually the clear glass giving views out. Dining spaces. The dining spaces had to be designed so that they suit a sort of winter population of 60 or 70 people, but don't sort of overawe you when there's only 15 of you in the winter. There's a pool table. This is within that glazed space, and that's within that same glazed space. So the bottom triangles are actually clear views out onto the ice. And then there's a staircase within a timber cylinder that rises up to the upper level. The timber cylinder is lined in Lebanese cedar because it's one of the few veneers that gives off a sort of pleasant smell. So we're always conscious of the sensory deprivations that people have in the Antarctic, and smell is definitely one of those. And the royal family, of course, is another one. So we made sure there was a picture of the Queen. This is the spiral stair leading up to the upper level. And then here, one of the quieter spaces for watching TV or playing games and so on. And then as you come along to the north end of the station, there's sort of office and control spaces. So this is the air traffic control and operations hub. There's a doctor's surgery with an ability to carry out small operations up to an appendix. The doctor also is trained as a dentist. These are the corridors with natural light coming through those holes in the roof there, and that you can see the use of the colour. And then here's one of the bedrooms, so with a desk, plenty of storage. The colours, again, all derived from our consultation with the colour psychologist, all with a view, but then at the same time with a blackout blind, so you can darken the space in the summer when you have 24-hour sunlight. And then this is the process of just jacking the modules at the end of the summer.
Next, the modules are dug out in preparations for jacking. The jacking frame is brought in. Snow is infilled under the ski.
Extending leg 1.
The ski is then placed back onto the heap of snow. This continues all the way along the length of the station. Once all the legs are up, the first jacking takes place. Then the process is repeated for the second jacking. And the melt tank is placed back in.
And there's the view of the station, fully elevated, ready for another winter. And here we see it in the middle of a winter, so you can see the rising snow level on the right-hand side and the big drift on the left-hand side. This is what it feels like at -40. Someone with a boiling kettle of water, just throwing it from that bridge link into the air, and you can see just instantly freezes. This is a view of the station during the Queen's Diamond Jubilee, where the southernmost Britons played croquet underneath the building in, I think it was about -35 and blowing at about 50 miles an hour. They also played cricket on the bottom right. This is the station emerging out of the winter, so covered in a hoarfrost, which is a very good sign because it means it's not losing any heat out of the envelope. So for us as a practice, it's been very good as a demonstration of British innovation, publicity, There's a book. The book is actually on sale if you're interested afterwards. It's also been on a coin and a stamp. A coin, however, that only has legal tender in the British Antarctic Territory. So fairly limited appeal, I guess. And then this is the best accolade for any architect, I believe. And I honestly found this on the internet just whilst trawling around the station. I discovered that a man in Grimsby who really loves the building has actually had it tattooed on his arm. Probably, of course, the best thing for an architect is that it leads to other projects. And I won't spend so much time on those, but I'll just show you very quickly where else we've been working in the Antarctic. The first project after Halle we had was designing a new base for Spain at Juan Carlos on Livingston Island, which is further north than Halle, just off the Antarctic Peninsula. It's a summer-only station. It gets very high snowfall in the winter, up to 3 meters. But then in the summer, all the snow melts. The wind blows in every single direction. There are quite rare plants or lichens and mosses which grow around the site. There's also a very fragile ecology, large colonies of gentoo penguins, elephant seals, the mosses I've mentioned, and then you get regular visits by leopard seals and whales out in the bay. So it sort of very different parameters within which to be designing, albeit still very cold and logistically challenging. And the seals, they just get absolutely everywhere. They will sit on the fuel pipes, they'll come up to the building, they'll come into the buildings if you don't shut the door. The base also has neighbours. So there's a Bulgarian base, which is about 2 or 3 miles by boat round the coast. And you can see bottom right, that's me visiting the Bulgarians. That's after we drunk half their store of raki for the winter. So it's not a tan. I'm actually probably not safe to go back in the boat at that point. And then these were our concepts for the station. So it wasn't going to be moved. It was going to stay in location. The wind, as I say, blows in every direction. So it's still elevated, but to account for this change in the snow level, it has an entrance at first floor level, but also an entrance at ground floor level, and then arranged in 3 arms, 1 for living and 2 for sleeping. And here you can see some of the earlier CGIs that we developed with a separate science building, so that provided a point of refuge if ever there was a disaster in the main habitat. And then the 3 wings connected with this central core, so everybody passes through that as a sort of not only a device for joining the buildings, but also for promoting social interaction amongst all the residents. And with big glazed elevations, so that people could really make the most of the spectacular scenery that surrounds the site. Originally, we had intended for the building to be an entirely glass fibre structure, so using more of the technology that's used, for example, in creating some of the new generation of airliner. But again, that was an untried form of structure within the Antarctic, and in the end, the construction was along the same lines as at Halle, with a steel frame, glass fibre cladding. So this is some of the smaller buildings around the perimeter being constructed. And on the bottom right and top, you can see the building nearing completion there also. We've, as I mentioned, taken part in a number of competitions. One of the most interesting, I think, was working on the Korean station, Jambogo. It was actually a competition in the end between Hyundai and Samsung, and we were teamed up with the Samsung team. The building combines the kind of bases of designing for an Antarctic station, which is that when you have low-level buildings, you want them oriented in line with the wind, because then you get a big drift just at one end. Whereas when they're elevated, you want them perpendicular to the wind, because then you get the drift set away from the building. So we combined the 2 principles. At the same time, the Koreans were very keen that the building should be inspired by Korean culture. So we looked long and hard at the sort of concept of gateway, to create a kind of gateway to Antarctic science, with the living space in the blue modules on one side, with the science on the other side, bridged by the sort of, I guess it's bedrooms on the left-hand side, bridged by the living space. And here you can see the kind of final designs for that project. It's also allowed us to move into the Arctic, where we've worked with the US on the development of a research laboratory, so just a very small building at their station, Summit Station in Greenland. Summit Station is really an inhospitable site. It's hundreds of miles from the coast, about 800 miles from the coast of Greenland. There's around 3 kilometers thickness of ice at the top of the Greenland ice cap. It has horrendous high winds, again, temperatures down to -50, -60. Just a small crew of 4 or 5 people who actually work here during the winter, although they can be relieved by plane every 2 or 3 months. And our design was for this laboratory, which the idea again was it was elevated to allow the wind to pass underneath. So very similar principles to Halle, but at the same time a kind of development of concepts, easier cladding solutions, and just this individual building, so no need for connections. We worked a little with NASA on ways to push the snow around the site. Because it's an atmospheric observatory, you can't have any kind of pollution next to the building, so you can't use normal bulldozers for pushing snow. So we needed to find a way of pushing it with electric vehicles, which is what NASA were also looking at the time. Looked into the forms of construction, and then here is the final design. It actually hasn't been built, but there it's still kept in the top drawer of the NSF, just ready for construction one day. And probably those principles informed other designs that we've done in the office, whether it's housing in Russia, whether it's for temporary museums in Washington. Also, through the work that we've done in the Antarctic, we have ended up collaborating with NASA on some really interesting exercises, one of which was looking at the net habitable volume that might be required for an astronaut on a long-duration mission, probably to Mars, on the basis that previous missions to the moon, people have been in spacecraft for relatively short periods, and they're really sort of just for transit, whereas traveling to Mars, you'll be living in the module for 9 or more months. The situation on Mars, of course, is very similar to the Antarctic. It's a featureless landscape. The craft that are needed to take you there are very small and determine the design through the logistic process. You have to wear very heavy and cumbersome clothing. And so through this process, we work with anthropologists, with doctors, with other architects, with human factor experts, to look at the base requirements for sleeping, for living, for exercise, for working, to eventually come up with a kind of base volume. Well, originally it was 18 cubic meters, but eventually went to 20 cubic meters, which is now used as the kind of basis by NASA for developing future designs for the module. I'm sure it'll get challenged in time, but that was certainly the start point. And one of the kind of really fun parts of the project was when you realize that you can work on every surface, so you can sit on the roof, and you can lie on the floor, and you can sit on the walls there, because it's all a zero gravity environment. You can use every surface. We've also started working again with the British Antarctic Survey as part of their new construction partnership. So British Antarctic Survey have combined their 2 ships into one big ship. You may remember the saga around Boatface, which eventually evolved into the Sir David Attenborough, which is the new ship now nearly ready for commissioning. But because it's much bigger, it'll do all the logistics, but also all the science in the ocean around the Antarctic for Britain. It means it'll visit the stations far fewer times. So there needs to be much more storage on the base. They need bigger wharfs and so on. So our role has involved looking at sort of infrastructure in a very sort of simple buildings at both Sydney and at Rothera. So this is Sydney Station, which is a very beautiful site in this, more or less in the sub-Antarctic. Again, only used in the summer, where we've developed just a very simple timber building lined in timber with all the living space on the upper level, and then all the science space, waste management and so on the lower levels, and then kept one of the existing buildings and reclad it for the power generation, sewage treatment and so on. And yeah, just a very simple, almost like a kind of Scandinavian or house or something you'd find in the New Zealand or Australian outback, I guess. And then at Rothera Station, which is Britain's largest station, which has a summer population of 100 people, again, there's a move to improve storage, improve the operation, and the building there, a very, very simple, I mean, sort of actually not really a kind of Antarctic building, but highly insulated, using solar power, incorporating air traffic control, and so on. And then our kind of most exciting Antarctic project of the moment, which is in its infancy, is the redevelopment of New Zealand's Scott Base. So you may remember that early historical slides showing Sir Edmund Hillary's hut, the one that was kind of like a kind of fawn and orange colour. Well, Scott Base has been New Zealand's base in the Antarctic since 1957, now supports a summer population of 86 people, and has science expeditions heading out from the base right across the Ross Ice Shelf into areas such as the dry valleys, which are amazing places for carrying out science research. This is an image of Scott Base. So that very first building is one of those smaller buildings in the foreground. Base was significantly redeveloped in the 1980s, and then there was one building added in 2004, but has had no redevelopment since then. But it's in an incredible site right next to the sea ice, where the sea ice meets the Ross Ice Shelf, with Mount Erebus in the distance. I was there actually only 3 weeks ago, and we were up in the helicopter just taking some photographs down on the site, just checking out the topography. It's quite a challenging place to build, because you've got to keep the existing base. It's on a sloping site. You can't get too close to the sea, but there are plants that grow round and about that we have to be mindful of. And then a big road which leads from the US base McMurdo, the largest station in the Antarctic, out to their airfields, following that road at number 6. And these are some of the issues to do with the station. It's on multiple different levels. Much of the equipment is really old. The services are really difficult to get at. It's got poor fire safety, snow drifting all around the site. All these are all different constraints. So people always think, oh, building in Antarctica, there's no constraints. But actually, this is almost as complex as building something in a city centre, because there are so many different parameters that we have to consider in the design. In developing our proposals, not only have we thought about our previous work in the Antarctic, the previous work of other architects in the Antarctic, but also started looking, I think, a lot more than we did before at things that have been successful in the Arctic. And in the Arctic, of course, there's many more architectural examples to draw upon. I love these two that I'll show you now. One is the administration building for the governor of Svalbard, designed by Jarman Visnies in Longyearbyen in the Svalbard archipelago. Just very robust structures, but making the most of the fantastic light that you get in the Arctic. And this, the Svalbard Science Centre, which is again a very beautiful building clad in copper with a timber interior and with a series of really inspiring spaces. And then here's some of our just very early sketches of what we may or may not be doing at Scott Base. And I think with that, that's a pretty rapid run around the Antarctic. I hope that's given you an idea of the kind of practical side of building in Antarctica. And thank you very much.
Wow, it was really, really impressive. Thank you very much for this very, very instructive tour of Antarctic architecture. I'm Francesco Bandarin, the co-director of the Polar Lab. And while you prepare a few questions, I think we have, maybe 20 minutes before 8 o'clock. I have one question. As you know, we're trying to look at all the facets of architecture in Antarctica. We started with the early settlements, even archaeology, and then the heritage. What is heritage? The huts. You show some of them. We looked at the second big phase of construction, which is the 1950s and 60s, with the scientific stations and so on. And then we look at the third wave, which is the 80s and 90s, when more people, more countries came to the Antarctic Treaty. And now the fourth wave is Hugh Broughton. Now, as time goes by, and because the erosion of these buildings is very fast, they become they are removed, or some parts of it become heritage. So first question is, what do you, looking at the contemporary, more modern architecture, 50s, 60s, and 70s, what do you think, what will be, in your view, some component that could, in the future, be considered heritage, because they did contribute to establish new principles of architecture, technology, and so on? If you have a couple of examples, I think you showed the New Zealand, and that's, I think, is a good example. But because you've seen many bases, maybe you have some suggestions on what future heritage of these bases is. Secondly, I noticed that you're working now on remodeling, reconstructing, and this is going to be probably the big business in the future, because most of the bases are from 80s and 90s, and 20, 30 years they're gone, right? Yeah. So of course, you know, maybe some countries will finance important construction like Halle or others, but probably most of the countries will try to renovate. So how do you match the principles that you have so cleverly developed for the new bases, which are entirely, you know, brought in, prefabricated? But I think we need to find some cross point between new technology and new design principles and what exists. I think this is a big challenge. So if you can elaborate a bit on these two things, and then we'll see other.
I think the question of heritage in the Antarctic is really intriguing. I think, you know, in the first wave of conservation, it was very clear what should be preserved, because the buildings, you know, were so intrinsically connected to the great exploration, you know, to the work, you know, whether it was Borchgrevink or whether it was Scott or whether it was Shackleton or Amundsen or whatever, you know. So those were, it was a kind of no-brainer that those were buildings worth preserving, not necessarily because of their architecture, but because of their whole historical, social significance within world history, I guess. I think the next generation from the 50s are interesting because they're still persevering that sort of sense of exploration, but they become more challenging. You know, it becomes more challenging as to, you know, do you keep doing that preservation? You know, the Buckminster Fuller Dome, for example, was a really interesting piece of architecture, but, you know, he built other geodesic structures, and that one, by the time it was eventually removed, was not in very good condition, and had potentially no real future at the South Pole Station. So I think we have to, you know, it is a question of size. You know, preserving Hut A at Scott Base, you know, it's a space, you know, a third or a quarter the size of this room. So there's a kind of rationale behind that preservation. There's a history still connected to it. I think when you're talking about, you know, preserving big components, it becomes more of a challenge. I wouldn't certainly ever envisage anybody preserving any component of Halle VI, for example, because it would just be mad. And you know, it was never, you know, there was never intended with that in mind. I don't suppose actually Edmund Hillary ever had in mind that Hut A of Scott Base would ever be preserved. But I guess he became such an important figure within New Zealand's own history that preserving that hut became an important part of the whole kind of Kiwi heritage. So I think people need to think, you know, very carefully. You know, is a pristine continent, we don't want to litter it with things if they don't have an important part to play in telling the story of scientific endeavour in Antarctica. Yeah, I actually don't know the answer, but I think it will be really interesting. I mean, certainly on Scott Base already, people are saying, oh, is there some part of the old base we should preserve? And I'm thinking, well, why would we? You've already preserved the most significant part. Why would you be preserving something from the 1980s? Maybe some great science occurred there, but it's not really telling any more of the history than the original first building. So I think it'll be an interesting subject, how that kind of sense of maintaining the historical line carries on, but what it is we should keep.
We should try at least to keep one module of LE6.
Wow, maybe.
But what about the reconstruction phase? I mean,
yeah, I think that's a really interesting thing as well. You know, obviously building an Antarctic research station is unbelievably expensive. Yeah. So the cost of Halle VI, only 2,000 square metres, but it was £50 million. So when it comes to cost per square metre, that's about as high as you can get anywhere in the world, I should think. So, redeveloping whole bases is a really expensive process, and we are seeing many more where people are adding a building. But of course, you run the risk then that the principles which underlie the original construction, which may be to do with managing the snow or just efficiency in operation, get slowly eroded because the next building is placed according to its specific need, but not necessarily according to the requirements of the whole base. So all of a sudden it creates drifts where no drifts occurred before, or it creates an energy burden where there wasn't one before. So I think it is definitely with Rothera, they have gone through a long master planning process to try and ensure that the sort of a slow development is managed within a kind of master plan kind of scenario, and I guess that's the key, and that's definitely the approach that's also being taken at McMurdo. McMurdo has 100 buildings, and they're reducing it down to 6, but reducing it to 6 over a kind of 15 to 20 year period, and I think it's really important to follow that sort of line of master plan to carry out these developments.
Very interesting. Okay, guys, time for you to raise some questions and hands if you want. Please. Wake up. Jean.
Thank you. That was amazing and fascinating. I guess rebounding on Francesco's question and remark, I would say that there's in terms of, this is not really to do with architecture, but with territorial occupation. I guess the entry point of a nation becomes in Antarctic history might become a place for preservation. So, for example, the Chinese who are redoing their Zhongshan station, there's conversations about keeping the first building because that's, of course, it sets a founding stone on when they began there. So it's not so much about the architecture, but about their own Antarctic history. And the same thing, I guess, in McMurdo, where you have these bars where people have built their social, personal histories. That's kind of also interesting. I had a specific question to do with Halle VI, which was, you mentioned that the water waste goes back into the sea. Mm. Does that mean that there's actually a tube that goes to the bottom of the ice shelf?
No.
Or does it go into the ice shelf itself?
Yeah, it just goes into the ice shelf.
Okay.
That's the simple answer. But there's a longer answer, which I am going to just briefly tell you.
Yeah.
Because not long after Halle was completed, they had a major issue because they lost power through the whole station. And they lost power for 19 hours at minus 55 degrees Celsius. So, I mean, the good thing was that it's very well sealed and very well insulated, and the temperature, I think, dropped by only 5 degrees. So it went from 20 to 15, so that was okay. But that was only, because they managed to sort it out in 19 hours. And the reason that they had the problem was because the pipe that drops the water needs to be a certain distance from the building, but it hadn't been moved year on year when it should have been. So the water was dropping very close to one of the energy buildings, and it's warm water, so it creates a big cavern. And so slowly one of the energy buildings had started to subside into the hole, and as a result it put the water pipes under tension, and they sprung a tiny leak, and those water pipes do all the cooling of all the generators. It was a design issue, I guess, and as a result the water coolant of each generator sort of kicked in and failed to work, so the generators shut down. So one after the other they shut down, and it then took the rest of the day to find that hole, patch it up, and then the next season they had to come and they had to excavate the hole, move the pipe, fill it in. So it's amazing how a tiny thing just can lead to so much work and maintenance. So that's the sort of, not quite the question, but nonetheless a big issue.
Yeah, really. Halle VI was shown at the Biennale in Venice in 2016, right?
It was, yeah.
In a pavilion, it was called the Antarctic Pavilion, joined to very futuristic designs by Hani Rashid, or I think Zaha did also did
she did, yeah.
some which was somehow imagining a life or possible life of people in Antarctica. Okay, let's talk about future. What do you think? Is that possible? Is that imaginable to have settlements in Antarctica? They're not permitted now, but you know, maybe a few years, for decades from now, this might be a case.
Yeah.
So what do you think?
And even though settlements per se are not allowed, you know, like in the Chilean base, the Chilean army base, there are family quarters. On the Chilean Air Force Base on King George Island, there are children who go to school. There are people born there. Yeah, so in a way there are kind of, you know, some micro communities who exist there. I mean, even
Halle became a tourist resort.
at times when the budget was really stressed, they talked about it. There's an amazing camp next to the Russian base Novorossiysk called White Desert, which is put up every summer, which is like geodesic domes, and you can go there to do a weeks-long exploration roundabout, or they'll fly you to the South Pole, and it'll cost you, I think it's $60,000 for a week's holiday, but it's sold out for years in advance. It's amazing. And you know, the rooms are all decked out like a kind of 5-star Scandinavian hotel. They fly in a gourmet chef from Cape Town, and you know, people go on holiday there. But will there be more of that? I guess it kind of depends. You know, that the treaty is intended to prevent that kind of thing from happening.
So you've not been asked to design a hotel so far?
No.
Any other question here? Yeah, please.
Hi, thanks so much for the lecture. It was fascinating. Looking at this is, as a design process for you as an architect, it seems like normally you would have some ideas on how things are and what living is like, but for you, I would imagine that you haven't been to Antarctica when you started your design process and you had to rely on the consultants. Now you have visited it. Do you think you gained quite a lot of own different design ideas, or was it enough for you to just kind of rely on the experience of other people to be able to design things in a more empathetic way?
That's a really interesting question. So it is true, when we did the first designs for Halle, we hadn't been to the Antarctic, so you did rely a lot on scientists who we met, who told us about the experience. After we won the competition, but whilst we were still designing, then I did go on the first visit. And it was quite interesting because there were some people who said, oh, well, the architecture's already established, why do you need to go on the trip? But actually, probably, of all the people who went on the trip, the engineers and myself and the builder, I probably did get the most out of it, and we instigated the most change. They might have been just tiny changes to do with, you know, storage in your bedroom, to do with, you know, a place to put personal things, or, you know, just things like having a flip-up mirror in your desk for doing your makeup, or, you know, whatever it was. There were just a whole series of little changes that we instigated. And I always find, you know, when we start each one of the new bases, you sort of think, oh, I wonder how similar this one will end up being to the last one. But the cultural dimension, but also the specific requirements of the organization mean that every one ends up being, you know, you learn from the last one, but you definitely aren't copying that many things. I mean, even we've done designs for bedrooms at Scott Base, and they're just completely different from the bedrooms at Halle. At Halle, they were all happy to share. At Scott Base, it's one of the key things. Everybody must have a single room, and it's kind of really interesting, you know, how that sort of, you know, countries do have a cultural dimension, and they're kind of embodied in these bases in a sort of microscopic way, which I find really kind of fascinating.
We have time perhaps for one last question. Yeah, there we go.
I was wondering about, as a designer, the experience of designing for places where people have imagined inhabitation in fantasy. You know, sort of your experience of life imitating art. We've seen many, many images of imagined habitation on Mars or Antarctica, the South Pole, et cetera. And so I think it's really interesting that you showed earlier settlements that looked like oil rigs, for example. So I was kind of wondering where your aesthetic references or things you were looking at, or how you navigated images from a kind of fantasy design in film, etc.
So it's a bit of a kind of meshing of loads of things, I guess. The engineering is a really big part of driving the design, but of course it's not the only part. There's a kind of science fictional element. Once you've sorted out the wind, you've sorted out the aerodynamics, you've managed to work out how to lift the buildings. The buildings still need some more form. So when it came to the outside, there were loads of kind of sci-fi movies that you've seen, and you think, oh, that's an interesting idea. And there are Thunderbirds and Star Wars. We had cutaway books of both of those sitting on the desk while we were designing away. And then when we were doing the interior, I always find the interiors are so interesting because actually they're very sort of first principle kind of spaces. So we really did we started with the bedrooms, because the bedroom is the kind of smallest space, so it actually dictates the sizes of the buildings more or less. And you just started thinking about the whole experience from the moment you wake up, and you swing your feet out of the bed. What does it feel like underfoot? Is it warm? Is it cold? Is it soft? Is it hard? Can I see out the window? Can I see anybody else out of the window? And then as I go out, do I need my own bathroom, or can I share with other people? Do I want to chat to people, or do I want to be in my little kind of bubble? And, we just thought about the whole day, and we just did loads of drawings, sort of sketches about moving around the building from place to place, and the experience and the moments that you might want to interact with people, and the moments you just want to get on with your business. And so in that respect, it's like starting designing a house and just thinking about the needs of the residents. So it was a kind of fusion between engineering, sci-fi reference, and then sort of first principle design, I guess.
Well, we have one more, but last, Patricia, short.
Sorry, I'm a short one. Have you had anybody living in Halle V and Halle VI? Have they give you any impression of the?
Yeah. Generally the feedback has been really good. It was interesting, how the feedback always relates to other aspects to do with the winter season. So there was one year that BAS were very particular about when you leave the Antarctic, you can either go through South Africa or you can go through South America. And there was a whole group who had thought, all right, we'll go out through South America and we're going to do this big trail through South America and we'll fly home from Colombia or something like that. And then BAS said, oh no, everyone is leaving through South Africa. So they were all absolutely furious. So they were given questionnaires and they just put big crosses across the whole questionnaire. And it wasn't really reflective of the building. But then the next years that we've done it, the feedback has been really good and really helpful. So yeah, I think they're the kind of buildings. We talk a lot nowadays about doing what we call post-occupancy evaluation, and these are the kind of buildings that need it more than anything else, really, because you want to make sure that you're not just transporting problems from one to the other. So we are lucky to do lots of them, but hopefully we learn from the mistakes rather than transport them to the next project.
Well, Hugh, first of all, thank you for throwing so much light into our Polar Lab, and really on behalf of all the crowd that is here tonight, and Giulia and the students, we would like, first of all, to thank you very much and applaud you very warm. I want to say one thing. Now that you are in the Polar Lab, we won't let you go. And we actually intend in the future to have one of the workshops on design principles and practices. So I hope we will continue our collaboration on this very, very exciting field. Thank you very much.
Thank you very much.
Thank you.
Thank you.